work done by Ruzba, Adam, Walid, Nolan, Prashant, and Mohammed from UMass and MIT. Okay, so we'll just start with a brief introduction and motivation. So it's this. So there's been an exponential growth in computing demand recently, and there's forecasted that data centers can consume up to 8% of global electricity demand by 2030. And so this growth in computing demand and the resulting energy consumption has enhanced its focus on climate and sustainability implications. And the focus has been magnified since the widespread adoption of generative artificial intelligence, such as ChatGPT and other large language models. And so now key stakeholders and policymakers and end users are trying to create direct incentives through caps or taxes on carbon emissions, and indirect incentives as well through social pressure to curb the climate impact of this unprecedented demand. And so if we look at the carbon footprint life cycle, the first is embodied carbon emissions or manufacturing carbon emissions. But for this work, we'll be focusing on operational carbon emissions, which is the consumed energy times the energy's carbon intensity. And so a significant portion of this operational carbon footprint comes from electricity usage, and some different strategies for reducing this carbon footprint can be improving the algorithmic and hardware efficiency, as well as improving directly the carbon efficiency. So for each unit of carbon emitted to more kilowatt hours of energy. So what we can do is use low carbon energy sources such as solar or wind, or for the focus of this work, we can run flexible workloads when low carbon energy is available. So basically in this graph of carbon intensity over 3 different locations, ideally we want to run the workloads when in the valleys of carbon intensity. And so in order to exploit the low carbon periods, what we do need is flexible workloads, such as batch jobs that are interruptible and can be suspended or resumed. And there are 3 main mechanisms to do this. The first is temporal shifting. So say that you can stop or start the job at different time periods. So this is basically a binary decision at each time slot. And ideally, you're running at low carbon periods and stopping otherwise. Next is spatial shifting, so moving the workload to a greener location that has less carbon intensity. And finally, focus of this work will be resource scaling. So instead of just a binary decision, we scale the number of allocated resources that could be assigned in each time step. And so just a brief overview of some existing work. The first work in this first row, carbon scaler, proposed by Hanafi et al. It's an offline algorithm, so it will assign resources, but it does need to know the length of the job length, and it also needs to know have a forecast of the carbon intensity over the time period. It also is unaware of a switching overhead of job scheduling. The next work called ramp on, ramp off, or RORO, as I'll refer to ongoing. So this one additionally it is independent of the carbon forecast, so it's an online algorithm, and also it considers a switching overhead for the objective function. So most crucially, both of these works, they do need to know the actual length of the job that's being scheduled, and this does have some issues which we'll discuss now. So estimating the job length can be a challenge in cluster and cloud computing. And so there's some unavailability of data on job attributes. There can be a lack of diversity in the available data, and there can be variations in the characteristics of the job submitted to the cluster over time. And a skewed distribution of users submitting the jobs means that job length predictions, even when using machine learning techniques, could be highly inaccurate and cannot always be used for scheduling purposes. And some work has shown that job length estimates on job submission time can have more than 140% mean absolute percentage error. Which is why for this work, the main additional consideration is that the job length is actually unknown. All that is known is between an upper and lower bound. And so the proposed work is a learn augmented carbon-aware resource scaling algorithm, or a LACS. So the problem that it solves is called online carbon-aware resource scaling with unknown job length. And so the main contribution here is that it does not need to know the job length exactly. What it does take in is a potentially inaccurate job length prediction. And this can improve the average performance when using the prediction, but it also tunes the usage of this prediction in order to retain worst case guarantees. And just moving into the problem statement. So what we have coming in is a job N, and it has some job length C, and this is bounded and a known deadline. In the learning augmented setting, we also receive a prediction C hat of the job length, which could be accurate or inaccurate. We also have some available resources from a resource cluster and some kind of constraint on resource usage per time slot. And the task here is to schedule the job over the period capital T, and the decision xt is the amount of job done at each time slot t. And so what we want is over the time horizon, the sum of xt will be equal at least c. And then the actual number of resources allocated for doing each job is f of xt, so some convex function of xt. And so this exact formulation of OCSU. So offline, we're given the carbon intensity, a parameter beta which can be interpreted as a linear coefficient that charges the algorithm proportionally to the amount of scaling between consecutive time steps. And this first portion of execution carbon emissions, first we have this resource scaling function as a function of the units xt allocated, the actual energy consumed per resource unit, and the carbon intensity, time varying carbon intensity. And the second part is a switching carbon emissions, which is this additional cost beta times the absolute difference in xt between each time slot. And then as for constraints, we do need to finish the job xt over the time horizon, and also the amount that can be scheduled in each time period is capped by dt as a rate constraint. And there are some means to ensure that for job completion that we can make sure the job is completed by the deadline t. So this is in the online setting, we determine xt in each time period without knowing the carbon intensity in each time slot. And so we can basically aggregate the execution carbon emission portion as a cost function gt, a convex cost function gt, plus the switching carbon emissions cost. And the main metric that we'll be considering here is the competitive ratio, which is the maximum over all possible instances of the cost of an online algorithm divided by an offline optimal, which knows all the information in advance. And so now we'll be going into the exact algorithm. So just to give some brief background, so OCSU is built on this online carbon-aware resource scaling, which does know the job length. And so in this railroad framework to solve it, basically it uses a pseudo cost based on threshold-based algorithm. So it has this decreasing threshold function phi of w, and this acts as an incentive to prevent the algorithm from waiting too long to run the job. So intuitively, if an algorithm naively minimizes the cost function g at each time step, it will be required to complete the job entirely during a compulsory execution period, and potentially bad for carbon intensity. And so basically, the pseudo cost minimization, it provides a framework for balancing the extreme options of allocating too much early on and waiting indefinitely. And basically, the important part here is that it will choose the amount xt based on two possible regions. And whenever the carbon intensity is attractive enough, the pseudo cost minimization finds the best decision to allocate just enough resources given the current carbon intensity to maintain competitiveness. So I guess the main takeaway here is that this algorithm is provably optimal in the online setting and also does not need to know the exact it is optimal even it only needs to know the carbon intensity function in per time slot. And it does not need a forecast. And so now for the main contribution, LACS. So it's built on this rural framework, but does not need to know the actual job length C. So so it combines the decision of two parts. A proportion of the decision is based on a robust application of RoRo, so it does not know the job length, and also considers a learning augmented part, which takes in the prediction of the job length. And so what this could do is it can improve the performance in the average case of consistency when the predictions are correct or close to correct. It also is robust, so retains worst case guarantees, even if the prediction is incorrect. And so this doing this does require some assumptions about problem parameters, so namely the per time step carbon emission function GT, the derivative is bounded, it has some bounded job length, and the switching coefficient is also bounded. So in this robust part, it's combining the decision of two algorithms, RoRo, Cmax, so assumes every job length has a maximal job length, and RoRo Cmin assumes the job length is minimal. And so in this first graph, the y-axis is the proven theoretical competitive ratio. So if the job length is known, this is the optimal alpha or optimal competitive ratio when the job length is known. And so now when we put in RoRo Cmax and Cmin, the competitive ratio is comparatively much worse because it is unknown, but it is still has a bounded competitive ratio. And then in order to improve the average performance, LACS also utilizes a solution for RoRo with a prediction. So it has a predicted job length C hat. And in this figure here, we want to draw your attention to the new purple line and the red line. For this purple line setting of consistency, LACS gets quite close to RoRo, which is optimal. And the reason it doesn't actually completely match RoRo is because it still takes into consideration the robust application of RoRo. And for the red curve, this is the robustness setting when it's given predictions that are quite inaccurate. Specifically, this is a setting where it predicts the job length is Cmin, but the job length is Cmax, but the prediction is Cmin in the worst case. And so in this setting, in the robustness setting, LACS diverges a lot from the optimal competitive ratio. And so now we'll be moving into experimental results. So it uses carbon intensity trace from electricity maps from 2020 to 2022. The carbon intensity forecasting error ranges from 0 to 40%. And then for job characteristics, the upper bound of job length can be from 1 to 6 with a deadline of 24 hours, and also assumes there could be a job length prediction error from 0 to 60%. And finally, it considers different resource scaling profiles of f of x. So as we proceed from P1 to P6, for doing the same amount of job, we need more resources and need to consume more energy as we change the resource profile. And so briefly, the baseline algorithms, the first is RoRo, which does know the job length. This is the optimal online performance, and it is impossible to do better than this when the job length is unknown. So we'll be comparing against this. The other four baselines, they differ based on whether or not they consider the carbon intensity or switching overhead. And finally, the main one to consider, LACS is the proposed algorithm. So here we'll be looking at CDF plots of the empirical competitive ratio in the x-axis of alg over opt. And so the tail end at the top illustrates the worst case performance, and the general area underneath highlights the more average case performance. And the further left, basically the further left the graph is in the first three graphs, the better the performance. And the fourth one is a summary of the first three, represented as an average. So as we increase Cmax, the maximum job length, the upper bound of the job length, the performance of all techniques decrease as they shift right. As having a higher maximum job length increases the uncertainty. However, the red curve LACS stays has the closest performance, the optimal online algorithm of RoRo. And so based on the summary, it's within 16% of offline optimal and very close to online optimal of 1.3%, and it has a comparative 31% reduction in carbon emissions compared to the carbon agnostic policy. And so if we also consider the effect of the switching parameter beta, a higher value of beta leads to higher empirical competitive ratio for algorithms that do not consider switching emissions. However, increasing beta does not affect the relative performance of algorithms that do consider the switching overhead, such as RoRo and LACS. And it has these improved numerical performance. And finally, briefly, it has a real-world consideration of discrete resource assignment. It requires some algorithm adjustments, and it compares against this carbon scalar algorithm, and it measures the effect as we change the carbon intensity forecast error. So when the carbon intensity forecast error is 0, carbon scalar does the best, but as this error increases, these learning augmented algorithms perform much better and are robust to prediction error. And so yeah, that's it. So this is the first learning augmented algorithm for carbon-aware resource scaling with unknown job length, and it has these theoretical guarantees and improved empirical performance close to offline optimal. And I think that's it. Thanks.
Okay, thank you for the presentation. Just a couple of questions. First of all, in your formulation, you consider this carbon like for prime emission, and in here I'm here. So in the literature, I think has been work on trying to just minimize the cost. Let's say electricity cost or any other operational cost, rather than carbon. But you consider carbon here, right?
Yes. Yeah.
So I'm wondering, what is the unique difference between minimizing general electricity cost versus minimizing carbon here?
Okay.
Can you hear me? Can you hear me?
Yes, we can hear you.
Awesome. So I didn't get the question clearly. So what is the other cost than the carbon cost? Would you please repeat that again?
Sure. In the literature, there has been work considered minimizing the, let's say, aggregate electricity cost or any other operational cost of the data center by considering this switching costs, etc. And so then in your work, instead of considering those costs, you're considering carbon. So I'm wondering, in terms of problem formulation, is there any unique difference?
The unique, yeah, it is like different than others. Like every cost function has its own characteristics. But in this work, we focus only on minimizing the carbon emission. But as you also mentioned, we can also extend this cost function to basically consider all these metrics like energy efficiency, carbon efficiency, and this kind of stuff. We can add it to the cost function. However, it would need more theoretical understanding of how to provide a somehow bounded algorithm that has a bounded worst case. But yeah, definitely we can consider all other metrics for the cost function.
Right. Well, if you say fundamentally they are very similar, then I think in your related work discussion, maybe you can also discuss the relationship to other existing work in the literature that has considered other cost functions. So that's my first question. My second question is that it seems they didn't touch too much, at least in the talk, about the particular theoretical framework you use to derive this optimal online algorithm. Are you using those a primordial type of approach, or you have some new algorithmic like framework to design online algorithms?
Yeah, so this work is, as we mentioned in the talk, is basically based on the RORO framework that knows the job length. And this work is also based on the analysis of the one-way trading, but with the threshold assignment. But yeah, basically it's not based on the primal dual, like classical primal dual, but yeah, it has some theoretical understanding and theoretical analysis of how to derive that threshold and this kind of stuff.
I see. Thanks. So my last quick question is that for typically, if you follow the use the modified or extended primordial framework, sometimes it's not very easy to prove the optimality of the competitor ratio, right? It's not very easy just to use that framework. So, but in your work, it seems to prove that your competitor ratio is optimal. I'm wondering, is it order optimal or is it exact optimal? And do you use any some newly invented like technique could be of a general interest?
Yeah, great question. So basically, our work, the LACS work, is not. We are not like saying that our work is optimal. Okay, putting that aside, based on the RORO that we built on, RORO is order optimal. Okay.
Thank you.
And yeah, sure.
Okay, thank you.
Sure. Yeah, happy.
What is the length of the time slot that you're considering? And what is the trade-off between carbon and your accuracy that is possible as you change the granularity?
So the time slot length is 1 hour, but I didn't get clearly your second question.
Is it possible to consider different time slots? Will the overhead of switching be reduced, and would it lead to what is the trade-off between reducing your carbon cost because of reduction in the switching overhead and the inaccuracy in estimating the carbon?
Yeah, so that's a great question. So that's the granularity is 1 hour because of the electricity maps trace that we had. That is that we have the average carbon intensity with the granularity of 1 hour. So if we wanted to extend or increase or decrease the time slot, we should have like more accurate data. But since we had only that data with the 1 hour granularity, that's why we only tested with 1 hour. But as a future work, we can definitely try with different time slot and different data sets that has like more accurate data for assuming like every 5 minutes carbon intensity in every 5 minutes. So that the results would also be interesting to show.
Thank you, but you can consider 2 hours.
Any more questions?
Yeah, we could also consider 2 hours, but I don't have like clear answer right now. What would be the results? But I'm assuming that wouldn't be like much difference when we consider 1 hour to 2 hours, because like there is some inertia between the changing the carbon intensity, like assuming like every 2 to 3 hours of the carbon intensity are basically in the same range. So we don't have like high variances in the low time slots. So I don't have like as I said, I don't have a clear answer now, but I think the results would be quite similar.
Okay, no more questions. Thank you for the presentation. And now we start the third paper.